Okay, so I've got, yeah, all. Okay, so first example was random walk on the Penrose tiling. So let me now give you a second example of the use of the what I'm calling the PHI theorem. So as I said in the end of the previous lecture, if we look at the continuous time simple random walk on ZD with natural weights, xt is the sum of independent random variables, and there are various probabilistic techniques that we could use to study it. Suppose now, though, that we look at a perturbation of the Euclidean lattice ZD. We choose in some fashion a subset E prime of the edges, and we look at the continuous time simple random walk associated with the edges where off the set E prime, we just jump across the edge at rate 1, but for the edges on E prime, we double the jump rate, and so the process jumps at rate 2. So any sort of sum of independent random variables method is going to break down really, because the process is no longer such a sum of independent random variables. On the other hand, the original weights, or the new weights and the original weights are bounded above and below by constants. So I'm going to use this symbol here to mean bounded above and below by positive constants. And it's quite fairly straightforward to show that volume doubling and the Poincare inequality hold for the new graph. We saw how to do it for ZD, and in fact, the same arguments are going to show it for the new graph as well. And so the continuous time simple random walk on this graph satisfies these conditions. And so using the parabolic Harnack inequality theorem, it also satisfies Gaussian bounds. And that's just reminding us what the PHI theorem says. And in fact, using the same ideas as that I just went through, we have the following theorem. So supposing we've got a weighted graph, and suppose that on this weighted graph, the continuous time simple random walk satisfies Gaussian bounds. Now I'm going to perturb the weights, and so C1 and C2 are strictly positive constants, and suppose that the new weights satisfy this relation here. So the new random walk jumps in a different way than the old random walk, and so it's not really easy to see using any kind of probabilistic method how we can sort of relate the new random walk and the old random walk. One might wonder if one can use some sort of coupling argument, but and I thought about that a bit at some point, but really it doesn't seem a viable method. Coupling works well if you've got two processes with kind of the same mechanics of transition starting in different places. But if you've got different transition mechanics, then even if you get them to go together again, they're going to wander off. And so I just don't think any sort of coupling argument is going to be able to handle a problem of this kind. But the analytic methods that I've described do handle this random walk quite easily. And so let's just look at how one does that. This is a sort of high-level proof using the PHI theorem. We use the implication Gaussian bounds to VD plus PI to deduce that this graph GA satisfies the two conditions, volume doubling and Poincare inequality. Then we do a bit of work to show that if VD and PI hold for GA, then they also hold for GA prime. It's almost immediate to see that that's the case for volume doubling. With Poincare inequality, it's a little bit more work, but nevertheless, it's true. And so we can say that these conditions are stable under perturbation of weights. In other words, if they hold for a graph GA and we have new weights A prime which satisfy these conditions here, then the Poincare inequality and volume Poincare inequality also holds for the new graph GA prime. So now we use the Phi theorem again. We use the implication VD plus PI implies GB for the graph GA prime to deduce that that graph satisfies Gaussian bounds. So what we see here is that these methods give us something which is not really, it gives us a way of attacking problems which, so to speak, the traditional probabilistic methods of looking at the heat equation or whatever are just not going to be able to handle. If we think about the equation satisfied by the transition probabilities or the heat kernel for the graph GA primed, it's going to be a different equation than the one satisfied for GA. And it's not at all clear how to use the fact that even that we have nice, perhaps, solution for the graph GA to be able to say anything about the solutions for the graph GA prime. So now I want to give you a flavor of some of the arguments used to prove the Phi theorem. As I mentioned, it's been proved in different ways by Giorgi, Moser, and Nash. And in my next lecture, I'll be saying a little bit about some of the Nash arguments. But today, I'm going to try and give you a sort of little sketch of what Moser did. And as I mentioned, there are two high-level conditions, PHI and Gaussian bounds, and one sort of lower-level condition, VD plus PI. And so not surprisingly, the easier arguments are the ones which show that PHI and GB are equivalent and that these imply volume doubling and Poincare inequality. And the hardest argument is getting from the lower level conditions VD plus PI to the two higher level conditions. So let's just give you a sketch of the sort of way things would proceed. So let's start by seeing how one can go from Gaussian bounds to the parabolic Harnack inequality. And so let's just recall the parabolic Harnack inequality. We're looking at this cylinder Q with little cylinders in it, Q minus and Q plus. And the parabolic Harnack inequality takes this form here. So this is for a solution, a function U, which is caloric. In other words, it's a solution of the heat equation. So suppose, first of all, that we have a function u yt, which can be written in this form. So pt zy is the heat kernel for the process. In other words, it's the probability starting in z that xt equals y divided by a of y. That's a solution of the heat equation. And we can sum it up over z in bx0r, so according to some measure vz. And any such summing here is going to give us a caloric function. So basically, the caloric function is obtained by taking the fundamental solution, as people say, of the heat equation PTZY, weighting it and adding it up over points here. And this little red circle here is a typical point in the ball. Now, if we look at the Gaussian bounds, they tell us that actually, if we look at for a point z here and a point y here or here, PTZY is bounded above and below by t to the minus. What I should have written here is mu a of the ball bxr rather than t to the minus alpha over 2. I'm sorry about that. But we get the same bound, and we would have to use the volume doubling to say that the two bounds that we get here and here are comparable. The Gaussian bounds give us that basically the term in the exponential is just a constant. So the Gaussian bounds tells us that these functions are all of about the same size for z in this ball here, and for y actually not just in the smaller ball, but in the bigger ball, and for t between a quarter t and a half and t. And if we feed this estimate here, sorry about the typos there and there, if we feed this estimate into equation 1 here, the parabolic Harnack inequality for this particular function pops out immediately. Well, that's just, we proved it for a sample function. And we would then want to know what is the most general caloric function. And the answer is that here we've looked at, so to speak, heat coming from a particular point Z and spreading out through this Q here. We also need to think about heat, so to speak, coming in from the side of the cylinder. So we would choose a point here on the side of the cylinder and look at a point sort of ZS and look at P T minus S ZY in this set here. And it's a little bit more work because the way I've set things up actually the side of the cylinder is a continuum. So we've got here in this picture discrete vertically in space and continuous time horizontally. But still the general caloric function in this set using various methods from potential theory can be written as, first of all, a sum of mass from the base of the cylinder plus also heat coming in from the sides. And with a little bit more work, but not really hard, one can show that the for the general caloric function, the Gaussian bounds lead you to the parabolic Harnack inequality. And by the way, if you ever find it hard to remember which way round the parabolic Harnack inequality goes, supposing you chose a point on the cylinder here where my cursor is, so heat just coming in from this point here, then the function u is actually going to be 0 for all times before this time here. So this side here is actually going to be 0, and then heat will have come in and there will be some positive thing here. So the parabolic Harnack inequality is not saying anything, it's saying that 0 is less than that. But this is a good way of remembering which way around the parabolic Harnack inequality goes. So that's a sketch of how you get the PHI from Gaussian bounds. Now let's look at how the parabolic Harnack inequality gets you to Gaussian bounds. And let me say that the whole argument, it's not really hard, but it takes a number of steps. And because the Gaussian bounds are a bit complicated, involving various different space-time regimes, and of course there are upper and lower bounds. So let me just give you the start of the argument. So we're going to fix a point, we're going to fix a ball Bx r over 2, Bxr, and the half ball B prime Bx r over 2. We're going to fix another point in our graph V, and we're going to look at the solution to the heat equation Uyt, which is Ptxy. And we're going to apply the parabolic Harnack inequality in the cylinder Q given, well, actually, by Bxr cross 0t. So Ptx over 2xy is less than the supremum over Q minus. That's less than CH times the infimum of U over Q plus. And if we choose a particular y prime in B prime, Ptxy prime is bigger than that infimum. So we get the inequality here. So you notice that we have no y prime on this side of the inequality and no y, but a y prime on this side. So we now multiply this inequality by the weight ay prime, and we sum over y prime in B prime, that should be not B, to obtain the following. So on the left, we have Pt over 2xy times the sum of the weights of the ay primes over B prime. And on the right, we have CH times the sum over y prime in B time, Ptx y prime, ay prime. So this is the probability starting in X that the process at time T is in the ball B prime. That probability is less than 1. So what we get here is less than or equal to CH. So we have this inequality here. Rearranging, we get this thing here. And so we've seen that we've got an upper bound on the transition probability from X to Y involving the some constants and the measure of the ball Bx0 R02. So that we would call a global upper bound on the heat kernel. And it's the beginning of the sequence of arguments that we would use to ultimately get the Gaussian bounds. So in the remainder of this second lecture, well, the next thing I'm going to do is I now want to sketch the argument that Moser used to prove his elliptic Harnack inequality. And I'm going to do it in the context of, first of all, I'm going to explain it in the context of a divergence form operator in RD. And then I will explain briefly how those methods generalize to other setups. So let's look at the setup and notation that we've got. Because of scaling, we can actually, it's going to be enough to prove Moser's Harnack inequality for a ball B01 contained in B02 in RD. And so we're going to write BR for balls of radius R with R between 1 and 2. Curly LA is the divergence form operator, which is acting on suitable class of functions mapping B2 to R. And H is going to be our target harmonic function. So it's a solution of LA H equals naught in B2 with H equals some prescribed function on the boundary of B2. And as is common in PDE analysis, we're going to leave out dx's to make our equation short, and so just write integral of f over it for integral f dx. And our aim is going to be to prove the elliptic Harnack inequality. The supremum over B1 of H is less than C times infimum over B1 of H. So there are a few ingredients which go in. The first is a Sobolev inequality. So there exists a kappa, depending on the dimension D, so that if we have a function of f from BR to R, then if we look at the integral of f to the 2 kappa, it can be bounded by a constant times the integral of f squared and an integral of the gradient of f. And Sobolev inequalities like this are well known in partial differential equations. The contribution of Saloff-Kost in his 1992 paper was to show that this Sobolev inequality actually can be proved from the Poincare inequality. So that's what I'm going to call lemma M1. Now, let's look at the next lemma M2. So now it's important that we're looking at, okay, so we're going to have to find ourselves controlling the integral of the gradient of a function f in terms of the integral of the function. And of course, for general functions, that's completely hopeless because we can find functions which are extremely rough and oscillatory, for which the integral of the gradient is huge and the integral of f is not huge. But if we're looking at harmonic functions or powers of harmonic functions, things are different. And so Moser's lemma M2 says that supposing we take a harmonic function h, we raise it to some power p, with p outside the region -1/2 to 1/2. So p could be positive or negative. And we're going to look at two slightly different sized balls, BS and BR, with sizes between 1 and 2. Then we can control the integral of grad G in terms of, first of all, the distance between R and S, and then the integral over of G squared. And so let me just sketch some of the main idea in the proof here. We choose what people call sort of bump function, eta. So eta is one actually, later we're going to be wanting to call these cutoff functions. So we choose a nice smooth function eta, which is 1 on the smaller ball and 0 on the slightly bigger ball, and perhaps I should write 2 there, but we want the gradient of eta to be less than a constant times r minus s. So you could choose a piecewise linear function and then smooth it out slightly to get such a function. So now we look at the integral of g squared on the little ball. That's less than the integral over the bigger ball of eta squared times mod grad g squared, because eta is 1 on the big ball, on the little ball. Now we do some integration by parts work. So we expand this gradient here using the fact that g is harmonic. We get derivatives involving p's and things like that. And after a certain amount of manipulation, you find that basically you can do an integration by parts and swap the gradient from the g to the eta. And so we get a relation here where we're looking at the integral over the bigger ball. And we know that the gradient of eta is bounded by r minus s. And so we get c over r minus s to the minus, that should be plus 2 there, not minus 2, sorry. And then the integral over br g squared. Actually, this seems a fantastically wasteful procedure because r and s are going to be very close together, and the gradient of eta is going to be 0 almost everywhere, at least everywhere on most of the mass, and just is large in a tiny little slip between s and r. So fantastically wasteful, though it appears to be, it's what Moser did, and as you'll see, it works. And an important remark is that these two lemmas work, although I've presented them in the context of divergence form operators, they actually work very generally on manifolds, metric spaces, and on graphs. And for example, for the continuous time simple random walk on a graph, we would want to replace the integral of grad f squared by this, what we can call the energy form, which I talked about a bit earlier today, which is the sum over x and y of x, y times the f of y minus f of x squared. So the ingredients that we go into Moser's proof, although I'm expressing them here for divergence form operators, actually hold in many other contexts also. So now here is the key to the first part of Moser's argument. So we're going to look at a ball of radius Rn, where Rn is 1 plus 2 to the minus n. So as n gets bigger, these balls are getting smaller and are decreasing to the ball of radius 1. Pn, the power we're going to be looking at, is going to be kappa to the n. And I'm going to take f to be either the harmonic function h or 1 over h. So let's start. We're going to look at the integral of f to the power 2pn plus 1 over bn plus 1. Well, pn plus 1 is just kappa times pn, so we can write things like that. Now we use lemma m1 for the function f to the pn to say that we can control it by the integral over bn plus 1 of gradient of f to the pn times mod fpn squared. Then we use the lemma m2 to get rid of this gradient, using here the fact that the function is harmonic. And so we get some constant rn minus rn plus 1 to the minus 2, and the integral of f to the pn squared. Rn minus rn plus 1 is about 2 to the minus n, so we get a 2 to the 2n here, and then we have the integral over bn of f to the pn squared. So if, like me, you come from a probabilistic background, this sort of argument really never works well for random variables, and it it looks rather alarming here. We want to control something, and we have this enormous term 2 to the 2n here, which which just looks as if it's going to sort of destroy any possible usefulness in this inequality. But no, if we now look at the norm of the 2pn plus 1 norm of the function, then we're taking powers to the 1 over 2pn plus 1. So you've got 2 to the 2n here times 1 over 2 times kappa to the n. And so this constant is actually very close to 1. What I mean by this notation here is this is the L 2pn plus 1 norm of the function f in the ball bn plus 1. I've defined it here. So we have this expression here, and it's easy to check that if we look at the product over n of these quantities here, we get some constant c, which is finite. And so by iterating, we get that the supremum, okay, these norms here, the balls are decreasing to b1, these pn's are increasing to infinity. So assuming some very mild initial regularity of the function f, like just being continuous, we end up with the supremum of f over b1 is bounded by the constant times the norm of f over b2 of 2, in other words, by this integral here. Now, remember that f could be h or h to the minus 1. And so what we end up with is the supremum over h of b1 is less than a constant times h squared. The supremum of h to the minus 1 is less than a constant h to the minus 2. So we've moved from wanting to control the function at a point to needing to be able to handle integrals of the function. So that's step 2 of Moser's argument. Sorry, that's the first main step of Moser's argument. So the second step in Moser's argument is to prove that we have an inequality like that. Let me just point out that the reverse inequality would be immediate from the Cauchy-Schwarz, but unfortunately, or well, I don't think one can use the word fortunately or unfortunately for mathematical facts which couldn't be other than how they are. But it turns out we need to prove things in the other direction. And this is where one needs to use the Poincare inequality. I should actually comment that although the lemma M1 that we saw earlier, some of course showed how it can be proved using the Poincare inequality, it does actually hold more generally in situations where the Poincare inequality doesn't hold. So we haven't really used the Poincare inequality at full strength of the Poincare inequality to get these equations here. But for the second step, what we want to avoid is the kind of bottleneck situation that we saw in our example of the two graphs z cubed joined at points, a place where the harmonic function is big in one region and small in another region. And the argument here is harder than the argument which I've shown you already, which is why I was lazy and spared myself and you going through the details of it. We need to use the Poincare inequality again. And actually, the original proof used the John Nuremberg inequality, but Bombier and Giorgi found a simpler argument, which is still a bit harder than the argument that I've shown you already. So they found an easier way of doing that. But I hope that by this sketch, I've given you at least some idea of how Moser's argument sort of gets going. And now, a remark, I've given the proof in the original context of divergent form elliptic PDEs, as it's sort of perhaps a bit easier to explain it in this form than for graphs. However, as I already stated, the two lemmas M1 and M2 also work for graphs, and one can use the same basic proof strategy. We can't use scaling any longer, so we need to look at balls center x and radius t to the nr now, with Tn playing the sort of same role as before, 1 plus 2 to the minus n. So one reason why I wanted to present Moser's argument initially in the context of divergence from operators in RD is that when we look at graphs, the discreteness gives us some additional problems when we now have a sort of transition at the point when 2 to the minus nr is less than or equal to 1. If we look back to lemma M2, these balls would then be the same. And so lemma M2 in its original form, the argument is just not going to apply. But one can use an argument using the local regularity of the graph to show that if you've got neighboring points and a harmonic function, then hx minus hy is bounded by a constant times h of x. And using that, one can get essentially the same as lemma M2 does, in other words, to control a higher power of the function by a lower power. So Moser's argument does all work in the context of graphs, and one can carry through his program to prove the Harnack inequality. So this is actually the end of my first lecture. I see I've I'm a little ahead of time. I went through material a little more quickly than I was expecting. Siva, what do you suggest? We could take a short break and I could start on my next lecture, or I can answer questions, or what?
Maybe we could have questions for some time and see how that goes, and then we can decide on your second idea.
Yes, right.
So if anybody has any questions, you can unmute and ask the question, please.
So I have one question. So the lemma M1, the claim is that Poincare implies Sobolev inequality, is it?
Yes.
And is this quite general? I mean,
yes.
I thought there are some extra assumptions. It's not needed.
Yes, I need to look again at Soloff-Kost's 1992 paper, but yes, I mean, the original paper of Moser had 3 ingredients. The Poincare inequality, well, used a Sobolev inequality on the space and a Poincare inequality on the space. And Soloff-Kost's contribution to what I call the Phi theorem was, first of all, he showed that the Poincare inequality on its own gave enough information that one could dispense with the Sobolev inequality, and hence, therefore, that one only needed the volume doubling and the Poincare inequality. So, sorry, let me take a step back. If we go all the way back in the history, Bombieri and Giusti used the EHI to prove a result about minimal surfaces. They needed volume doubling, the Sobolev inequality, and the Poincare inequality. So they took Moser's ideas and generalized them into a manifold context. Then 20 years later, Soloff-Kost showed that the Sobolev inequality could be sort of removed, and you just had the Poincare inequality and the volume doubling condition. And then he also then showed that once you had the Poincare inequality, the parabolic harmonic inequality, that gave us both volume doubling and the Poincare inequality. And so he actually therefore gave the characterization of the PHI.
Okay, thank you.
Other questions?
Just one question. These Harnack inequality for these functions, does it imply some inequalities for the exit measures?
Sorry, can you say it again? I didn't quite catch what you were saying. Does it imply some inequalities for?
Yeah. You see, suppose you take a point X and a domain, okay?
Yes.
You can look at the exit measure, right, from the domain on the boundary.
That's a very interesting question. Now, I'm going to see if I can get the whiteboard here.
I think you stop sharing, Martin, and then start the whiteboard. Yeah. Now you can start the whiteboard. Share screen again. And
Okay.
Whiteboard.
That's wait a minute. Oh yes. Okay. Okay. So I mean, this is a very interesting point. So we look here at a ball, and we are looking at the exit measure. So the question is, if we look at the probability of leaving the yes, so the Harnack inequality tells us that the probability of leaving the set in this little area here is comparable to these 2 points. What the Harnack inequality, slightly surprisingly, doesn't tell us is give us any kind of nice control over the exit measures. So supposing we look at a ball in RD, oops, perhaps I shouldn't try and write this. So supposing we look at a ball in RD, so it's a ball with a nice boundary, then we know that Brownian motion leaves that ball, the harmonic measure is nice and smooth. We might ask then, if we've got a divergence form operator A, well, where the functions aij are bounded, shall we say, between 1/2 and 2, we might then hope that the Harnack inequality tells us that the exit measures for the ball are similarly nicely behaved. But somewhat surprisingly, that's not the case. We can actually choose the measure. This is a well-known paper in PDE, but I can't give you a reference right now. We can choose the functions aij in such a fashion that actually the harmonic measure for the process associated with the divergence form operator LA is actually singular with respect to the Begg measure on the boundary of the ball. So that's a bit of a surprise. The process still satisfies Gaussian bounds, but nevertheless, its behavior at exit times is bad. When I give my final lecture, I'll be saying something about the instability of the Liouville property as we perturb the weights A, and that is actually that these harmonic measures are can be badly behaved. It's a little odd. The first time the process hits the boundary, it can behave in a very odd way. But if we can sort of look at the process as it continues to move through the boundary, the sort of parabolic Harnack inequality in the Gaussian bounds means that the process is sort of smoothed out. So its first hitting is odd, but its general behavior is not odd. So it's surprising, and I can't really give you a sort of intuitive explanation of why the two things are different. The thing is that we can use this if we have an A which is not identically, and we look at the operator grad. I mean, I can explain roughly how the argument goes. We look at the operator grad A grad. If we think about Brownian motion, it sort of moves in equal mass energy, so to speak, in all possible directions. We can choose A in such a fashion that the process has more of a tendency to move in one direction than another direction. And so we can use that, that behavior to sort of steer the process in towards a bad set. So that's roughly how the argument goes.
So does it have anything to do with the nature of the domain, or that can happen?
Sorry, can you say it again?
Does it have anything to do with the nature of the domain, or for any domain it can happen?
It's, well, I mean, I wouldn't like to say it can happen in every possible domain, but that sort of phenomenon can occur in a lot of different domains. It's not specifically tied to the nature of RD or anything else.
Thank you. I see. Very interesting.
Are there any other questions? Martin, I have a notational question on page 27 of your slide.
Okay, let's clear the drawings and try and go back to
28.
Okay. Okay, your page is this the one?
No,
This is not the page.
It's the one with GB to PHI.
Yep.
This one. So the red ball is BXR, is that right? Or what is the red ball?
Well, the red point here is supposed to be the point Z.
Point Z.
It's supposed to be just marking a particular point.
I see. And then this box is T and R squared, is that right? T on the X.
Okay, yes. So the vertical is BXR.
I see, okay.
Horizontally, I mean, this is supposed to be the same space-time cylinder as we had before. So vertically we have BXR, horizontally we have 0T squared.
I see. And what are the blue circles?
Okay, so sorry about this. The blue circles are supposed to represent possible points Y that we want to compare.
Possible points Y you want to compare. I see. Across the
Yes, so we want to compare the solution at a point like this with the solution at a point like that.
Oh, very nice. Okay, very good. And
so
then,
sorry.
The last notation question I had was the following: that so you have Gaussian bounds. That means you have 1 over the weight of the ball times exponential on both sides, right? Is that right? That's right.
Yes. Let me look at. Yep.
Right. So then, how do you get t to the minus alpha? You throw away the exponential, and then the volume of the ball is of the correct order. Or
okay. So I'm sorry about. Yes. If we look here, going back forward here and dealing with my unfortunate misprint.
Yeah.
Okay. So perhaps what we get is the exponentials.
Right.
Because the distance here is about r squared, and the time is bigger than a quarter r squared, the term in the exponentials are just e to the minus a constant. So just give us another constant. So the only term we get in PTXY is a constant over the measure of a ball of radius about t to the 1/2.
Right.
And actually, we would need to compare the measure of 2 balls of radius C1 t to the 1/2, a measure a radius C2 t to the 1/2. And so in order to get the upper bound and lower bound here comparable, we would need to be using the volume doubling property.
Yeah, but what's the role of alpha?
Alpha, well, this is just wrong. Let me see if I can, how do I, annotate, there we are. So basically, sorry about this. What we ought to have here in both cases is 1 over mu A.
B
That's
of
a terrible A. Sorry.
B of
B.
ball of radius t to the 1.
Yes. Let's call it just B prime. Yep. So I guess those alphas came from. I copied the slide from something there. I shouldn't have.
And then in the next slide, I have a question. Can you erase the drawings? Or you can leave it. It's not a problem. Go next slide.
I think. Okay. I need to do that before I can move on to the next slide. Yep.
Okay. So now from this, somehow you will get a Gaussian bound. Is it? There's PT by 2 y.
Okay, so I didn't at all explain how one gets the Gaussian bound. Essentially, one does a sort of iteration argument. Okay, I'm just trying to think of the, well, there are several ways of doing it. Actually, getting the Gaussian bound, the Gaussian lower bound is easier to explain than getting the Gaussian upper bound. With another sort of similar argument using the parabolic Harnack inequality, one can also get the transition probability is bigger than a constant over something similar. And then if you've got your, supposing you now want to prove, let's use this slide here. Supposing you want to now show that you want to look at getting from a point X to a point Y in a time T, then basically it's only of interest if the distance between dxy squared over T is large, because otherwise if the constant is of order 1, then the heat kernel is already going to be just this order here. So what one does is you look at a collection of smaller balls where you choose the size rather precisely in terms of the distance between X and Y and T, and you look at the probability of the process going from here into this ball here. The lower bound tells you that there's a reasonable probability of that transition. Then you look at the probability from going from here to here, here to here, and so on. And so you get a chain of balls and doing the calculations appropriately, you find you get a Gaussian lower bound on the transition probability. It's a bit surprising that one can get what is essentially up to constants, the best possible bound, but by actually choosing a fairly narrow chain of balls here, probabilistically the intuition is that we're looking at the process moving a fairly long way in a fairly short period of time. And if it's going to make that journey at all, it's more or less best possible. Most of the probability comes from it running in a cylinder and at a more or less constant speed along this chain of balls. So that's how you get the Gaussian lower bounds. For the Gaussian upper bounds, a probabilistic argument would be again to take a chain of balls and to say that it's difficult for the process to move too quickly. And so the chances of it going from X to Y in a short period of time, it has to make a lot of jumps. It has to make a lot of unlikely movements over a short scale. And one can bound that by, you get a collection of probabilities which you can bound using the binomial theorem. And again, if you've chosen your little balls and your little times in the right way, you will get out a Gaussian bound. There are other more analytic ways of getting the same argument.
Thank you. Yeah. Are there any other questions?
Yeah, just one more question. Maybe I'm a little bit confused. You see, in case of R2, Doops proof that positive harmonic functions are constant goes via recurrence, and that a positive martingale convergence, right?
Yes.
F of BT. Okay. But here, instead of that, we have used Harnack inequalities And is it, I'm a little confused, that recurrence did not play any role,
No, I mean,
or there is no recurrence?
the
I'm
Harnack
confused.
inequality, no, the Harnack inequality applies both for R2 and for R3. So it's the original Harnack inequality. So Harnack inequalities are not directly connected with transience or recurrence. I should say that in the recurrent case, all these inequalities turn out to be much easier to prove. Which in classical analysis, of course, is just R, which is really easy. But in the case of dimensions 1 or 2, actually, the regularity results of Moser and so forth that Moser proved had already been proved by other methods using special properties of R2. So the challenge was really to prove these things in higher dimensions.
Thank you. I see. Nice.
Okay, I think we've run well past time. So maybe we can all unmute ourselves and thank Martin for the first 2 lectures. I request everybody to unmute. Okay, so Martin, I think we are 10 to 5, so I think we have done well with time as questions. So we will meet on Thursday, same time at 9:15.
Yes. Right. Thank you.
Thank you very much, and we'll see you all. Bye bye.
Right. Goodbye.